Okay, this video is going to talk about the derivative of polar curves. Now, we've talked about the area of a single polar curve. We've talked about the area between two polar curves. Now, all that's really left is how do we find the slope of the polar curve? So the derivative. Okay, so your target is students will determine the derivative of a polar curve using implicit differentiation to determine the slope of the curve. It's kind of redundant, but we're going to kind of talk about that today. Okay, so when it comes to the slope of any curve, whether we're in rectangular form, polar form, or what we'll learn as parametric form next week, the derivative always comes down to the exact same thing. The derivative, or the slope of a curve, not the derivative, but the slope of a curve, always comes down to dy over dx. The problem is we don't have a y or an x in our polar curve equations because our polar curves are also often something that looks like this. Okay? Which means our points are r values, our radius, and theta values, the angle of rotation, where theta is the independent variable. Okay, so this is kind of where the conversion equations come in. So on your page 230, at the very bottom, there's conversions that we use. The first conversion talking about x equals our cosine theta, which makes sense because x is our cosine value, and y equals r times sine theta. Again, makes sense on our unit circle, or y value is the sine. Okay, so we kind of use that relationship for these conversions. In the video that you guys watched this weekend, or this past weekend, it talks about the conversions and how we convert from polar to parametric and vice versa. Okay, so it shows you that basic idea of a polar curve. But because these conversions are in terms of x and y, they now have an x and y in them, we can actually take the derivative of these conversion equations to get our dy over dx. Okay, remember our independent variable in these equations is still theta. It's not x, it's not y, it's still theta. So when we take the derivative of this, we take the derivative with respect to theta, which means if I take the derivative of the first equation, I get something that looks like dx over d theta, which is nice because that dx is present now in our equation. And if I take the derivative of the second one, I'm going to get something that looks like a dy d theta. Again, nice because that dy that I need for the slope of a curve is present. So if I go back to this idea of dy over dx, well, dy is just the change in y, but dy d theta is also the change in y. So I'm going to replace that. Okay, because it is the change in y with respect to the theta value in the actual equation. Okay, where our bottom, or the bottom of our dy over dx, is actually the change of x, which in polar form can be rewritten as the change of x with respect to theta. Now this is just calculation or division of two fractions. Knowing what we know from algebra, we know that we can simplify this by taking our numerator and multiplying by the reciprocal of our denominator. And because of this simple fraction operation, our d thetas are going to cancel out, and we're left with that idea of dy dx. Okay, so we're going to use this property right here to actually find the slope. But that means coming back and actually taking the derivative. If we look at our x equation, let's start there. So x is our cosine theta. Well, r in polar form is a function. Okay, r is in terms of cosine. That's like saying f of x equals cosine x. So if we say f of x equals cosine x, okay, that means that this part right here is a function itself in terms of x. We write the derivative of that as f prime. Okay, and then we take the derivative with respect to x of the other part, and we get that this is our negative sine of x. Okay, so we're going to use that same property except with r and theta. Okay, so if I take the derivative of this with respect to theta, I'm going to get something that looks dx d theta, which is what I want. And then because both of these are functions, that's like saying f of x times cosine x. Well, times implies that we're going to use the product rule here. So that's exactly what we'd have to do to take the derivative of r cosine theta. So our product rule says take the derivative of the first. If I take the derivative of f of x, I get f prime. Same thing here. If I take the derivative of r, I'm going to get r prime. Derivative of the first times the second plus derivative of the second, which is negative sine, times the first. I get something that looks like that. I'm going to clean that up really quickly. R prime cosine theta. We're going to have a minus r sine theta. So that's our derivative of x with respect to theta, which is one part of our equation. Okay. And then I'm going to do the same thing with the y equation. So y equals r sine of theta. And we're going to do the same thing, use the product rule to find the derivative with respect to theta. Excuse me. So dy d theta equals, I apologize. That derivative of r gives us r prime. Derivative of the first times the second, sorry, not, it's cosine, times the second, plus derivative of the second, and there's the cosine, times the first. I'm just going to rewrite that really quickly. So r prime sine theta plus r cosine theta. And what we're going to do is we're going to take the derivative of dy d theta and divide it by the derivative of of dx d theta. And that's how we get the equation for finding the slope of a polar curve. Okay, so that's where the equation comes from. Tomorrow we'll talk a little bit more about it, and then we'll actually do some problems. So if you have any questions, come in and see me.